Okay, to write a K for any chemical equation, expression like K equals this, so we're going for. Now, these things are on, the actual formula is right here on your reference sheet, so all of this is something you can get from your reference sheet. I just want to explain it, talk about it, what's not there, what they are, where we see it. It's K is like all over this thing. These are capital Ks. There's one other capital K for K is in Kelvin, a temperature. It's not this. There's a lowercase k, another constant, a rate constant. It's a little bit different. This is an equilibrium expression. All right. So, all right. All right. The Ks that we're talking about. There's the K in electrochemistry and electrochemical cells. It's a capital K. This is on the reference sheet. This K has to do with weak acids and bases. These are Ks, an equilibrium expression for Ka and Kb, the autoionization constants. There is Ks that have to do with water, Kw, which is also on your reference sheet. All right. There's the ones that have to do with insoluble salts. That's your Ksp. All right. That is not on the reference sheet, but you'll need to know how to write the expressions for those chemicals. And then the final one is with chemical systems, where they're like a reaction chamber, or it's like a reaction that is at equilibrium. These are your Kcs, your Kps, sometimes just plain old capital K. So all of these Ks, what we're going to do today applies to how we write these expressions. K equals the subscript, the A, the B, the W, KSP, all that may change, but this applies to all of them. One thing I want you to that applies to all of them is that they're all temperature dependent. So if I change the value of change the temperature, then I'm going to be changing the K value, the number. These K values they're numbers. It's a positive number. You shouldn't get a negative K. They can be big or small. All right. And they're unitless. K values don't have units. Okay. But they're a number, positive, always positive. They're big or small, and they're unitless. This video is not really about how to calculate them, just about how to write the expressions to calculate them. All right. Now, all equilibrium expressions are all K equals. They're all products over reactants. You could think of them like a percent. They're not really a percent, but you could think of it like a percent. It's going to tell you It's going to tell you something about a reaction, which we'll get into in another video, and that's why I like to think of them like percents. All right. Now, one other thing, in these expressions, there's no solids or liquids. They're not part of the equation. And if we had a general equation where A, the coefficient is a lowercase like this, all right? This double-sided arrow means you're going to have the K expression. The K expression would be equal to, this is Kc, it means K concentration, all right? The products goes on top, all right? So the first product is this, Kc. You'll notice it's the concentration of C raised to the subscript of the C. I'm going to multiply that by this, the G1, all right? And then the reactants are going to go on the bottom, all right? Where the exponents become your coefficients, all right? Now, for this, these brackets are for concentrations like molarities, okay? Now, you'll see other ones where they're in parentheses. That, And if you notice, I'm going to pause it. You'll notice right here, they're in parentheses. This means they're talking about a partial pressure, all right, of various things. And it's written the same way as this, except it's pressure of C, the partial pressure of C raised to the coefficient of C, all right? So the parentheses are for partial pressures. And here's what, hold on. So the parentheses, partial pressures, here's the expression, all right? These two go on the top, all right? And then the other two would go on the bottom. So it's the pressure, partial pressure of A raised to the coefficient of A times the partial pressure of B to coefficient of B. All right? Now, let's go over some problems. All right. What's the expression of this? All right. Let's do it as pressure. So Kp is, here are my products. So partial pressure of CO times the partial pressure of H2 raised to the second all over the partial pressure of methanol. Okay? And that's the equilibrium expression. All right? Now, let's say, here's another example. What if I had this experiment going on? What's the K expression? I've got dry ice and gas, carbon dioxide, total brain cramp there. It's in a sealed container. So it'd be CO2 solid, CO2 gas, all right? So my Kc would be just the concentration of CO2 gas, all right? And I really all over 1, so that would just reduce to Kc is the concentration of CO2, all right? And go back. The reason this is because this is a solid, so it doesn't enter into the equation. All right. I got two gases forming two gases, diatomic forming two compounds. What's the Kc? What's my concentration going to be? Well, it's going to be equal to my products, Hi, the concentration of Hi, squared over the concentration of all right. And these aren't typically the gas. You're not going to have concentrations, so that's not. But that's how you would write it. It'd be Kp, and it would just be the same thing with in terms of pressure, like that. Okay. Carbonate ion is a weak base. So one last example. What is its equilibrium expression for it acting as a base? So I would say CO3, 2 negative, plus H2O. So it's acting as a base, so that means it's going to accept a proton. So it's going to be HCO3 negative 1 plus OH negative. Now this is aqueous. This is aqueous, and this is a liquid. So my Kc would be my concentration like that. Okay? Let me know what I can do to help. All right, bye.